Imagine you're a typical 40-year-old woman walking into a clinic for a routine mammogram. A few days later, the doctor calls. The test came back positive. They explain that this specific test has a 73% sensitivity rate, meaning if a patient has breast cancer, the machine correctly detects it 73% of the time. Given that score, how likely do you think it is that you actually have cancer? It feels incredibly high. But the reality is completely counterintuitive. Despite that 73% accuracy rate, a positive test means you still have less than a 1% chance of actually having the disease. This massive gap between our gut feeling and reality is called cognitive asymmetry. Our brains are highly tuned to calculate what statisticians call forward probability, moving from a known cause to an expected effect. If you see a baseball flying toward a window, you can predict the glass will shatter. But we are remarkably bad at inverse probability. That means looking at a final effect, like a shattered window on the ground, or a positive medical test, and trying to trace it backward to a specific cause. Was it a baseball? A burglar? The wind? Because our intuition wildly overestimates inverse probabilities, we routinely panic over statistical false alarms. To fix this glitch in human cognition, we need a mathematical framework that forces our brains to think backward accurately. That framework was developed in the 1750s by an English minister and amateur mathematician named Thomas Bayes. He was obsessed with finding a precise formula that could deduce a cause strictly by observing an effect. This diagram shows the thought experiment Bayes designed to test his ideas. Imagine shooting a billiard ball on a table, letting it bounce blindly. If you already know the total length of the table, represented by L, predicting the probability that the ball stops within a specific distance from the edge, marked as X, is straightforward. Now flip the script. Look at the bottom diagram. Suppose you observe the ball's final position, X, but you have no idea how long the table is. What is the probability that the table is exactly 50 feet long, or 100 feet? It's a dizzying problem. A shorter table makes a resting spot near the edge more likely, but a longer table is still physically possible. There are simply too many potential competing causes for this single observed effect to solve in your head. To solve Bayes' puzzle, we have to strip away the physics and look at pure data. Let's imagine a local tea house that tracks whether its customers order tea, scones, or both. This table shows the raw order data for 12 customers. Notice that data itself doesn't care about cause and effect. It doesn't matter if the customer ordered tea first or scones first. The spreadsheet merely tracks the relationships. We can read this data in the forward direction. Out of 12 customers, 8 ordered tea. Of those 8, half also ordered scones. That means 4 out of 12 customers, or 1/3, ordered both. Now, let's calculate it in reverse. If we start with the 5 people who ordered scones, we see that 4 of them also ordered tea. 4 out of 12 is still exactly 1/3. The final proportion remains identical, regardless of which event you started with. Because both directions lead to the exact same outcome, you can set them equal to each other. This creates an equation where the probability of ordering scones given you bought tea balances perfectly against the probability of ordering tea given you bought scones. This innocent piece of algebra does something incredible. If you know the reliable, easy-to-find forward probabilities, you can plug them in and mathematically deduce the elusive inverse probability without guessing. We can now apply this exact logic to our 40-year-old patient. We need to find her inverse probability, the chance she actually has cancer given that her test is positive. To do this, we need a starting point, which statisticians call the prior probability. Before any testing happens, the baseline rate of breast cancer for a typical 40-year-old woman is roughly 1 in 700. Next, we factor in the test's error rate on healthy patients. Even when a woman doesn't have cancer, the mammogram will still trigger a positive result 12% of the time. This graphic shows those numbers colliding in a sample of 3,000 women. The massive healthy population's 12% error rate produces 360 false positives. These completely drown out the tiny handful, just 3 women, who test positive and actually have the disease. Bayes' rule forces us to see the full picture. In a low-risk population, a positive test is overwhelmingly more likely to be a statistical false alarm than a medical death sentence. The true utility of Bayes' rule is its scalability. If our patient has a specific genetic marker that puts her at high risk for cancer, her prior probability changes. You plug that new baseline into the equation, and suddenly that exact same positive test leaps to a 1 in 3 chance of cancer. It functions as an algorithm for your worldview. Every time you encounter new evidence, you update your prior beliefs, run the calculation, and arrive at a sharper, more accurate picture of reality. This iterative process of updating beliefs based on continuous data is exactly how machine learning and artificial intelligence function today. Computers use Bayesian logic to evaluate massive streams of evidence and trace them backward to their likely causes. You interact with this math constantly. It powers your email spam filter, Google search algorithms, and the backbone of weather forecasting. It also operates in incredibly high-stakes environments, like forensics. When Malaysia Airlines Flight 17 was shot down in 2014, investigators used a software called Bonaparte. It relied on Bayesian networks to piece together partial DNA matches from distant relatives, successfully identifying the remains of the victims. What began as a minister's mathematical thought experiment about bouncing billiard balls evolved into a digital reasoning engine capable of deducing the hidden causes shaping our world.